Hi everyone. In this video, we'll be discussing separable ordinary differential equations. In particular, we're going to learn about a new type of equation called a differential equation. We'll use methods of integration, which we've seen previously, to solve certain classes of differential equations, and we'll apply our mathematical skills to solve real-world problems. So first, what is a differential equation? A differential equation is an equation which relates an unknown function and its derivatives of various orders. So for example, on the screen here, you see two different differential equations. So in the first differential equation, the idea is we're looking for an unknown function u of x, whose second derivative plus 4 times that function is equal to 0. Now we can observe here that the function u of x equals sine of 2x is a solution. Okay? So in particular, right, if I take a first derivative, that will give me 2 cosine of 2x. And if I take one more derivative, that will give me u double prime of x is negative 4 sine of 2x. And now I observe that u double prime of x plus 4 u of x is, so u double prime is minus 4 sine of 2x plus 4 times u of x, that's sine of 2x, and those add together to give me 0. So in particular, it's very easy to check that this particular function is a solution to this differential equation. I simply calculate the necessary derivatives, plug everything back into the left-hand side here, and note that, in fact, when I do that, I get this is equal to 0. Okay. Now, it actually turns out that's not the only solution. Okay, so we could repeat this process, this time taking u of x to be cosine of 2x. Now, if we do that, we'll get, skipping a few steps, we'll get that the second derivative is minus 4 cosine of 2x. And so u double prime of x plus u of x will again be equal to 0. Sorry, u double prime plus 4u of x is 0. Okay. And in fact, it turns out that any sort of combination of those sines and cosines will work. So in fact, anything of the form some constant times sine of 2x plus some other constant times cosine of 2x will also be a solution to your differential equation. So this first differential equation has many, many solutions. For any constant C1 and C2 that you pick here, these will be solutions. The second differential equation says I'm looking for an unknown function y whose derivative is equal to 1 plus that function squared. Okay. Now again here, if I give you a candidate, you can check to see whether or not it is a solution. So for example, maybe I asked you if y of x is equal to x is a solution. Well, you could check that. dy dx would then be 1. And so plugging it in, you would be asking, is 1 equal to 1 plus x squared? And again, here you might say, well, sure it is if x is equal to 0. But I'm thinking of these as functions. So in order for this equality to hold, I would want it to be true for all values of x. And so these two clearly are not equal for all values of x. And therefore, y of x is equal to x is not a solution. So you can check that that is not a solution. You can also check to see that tangent of x is a solution. So dy dx here would be the derivative of tangent is secant squared. And now if you plug this in, you would get on the left-hand side secant squared of x. So that's my dy dx, and then is equal to, I want to know if these are equal, is that equal to 1 plus tangent of x squared, because tangent of x is my y, so I'm plugging that in here. And this is a trig identity, right? We know that secant squared of x is in fact equal to 1 plus tangent squared x. And so this is in fact a solution. Now, we'll actually see it's not the only solution. We'll see in a bit what the other solutions are. But it is a solution to this differential equation. So differential equations are equations where the unknown is a function and the relation involves that unknown function and its derivatives. In this case, it involved a second derivative and the unknown function. In this case, it involved the unknown function and the first derivative. It can involve derivatives of any order, so 19th derivatives if you wanted. But this is just the general idea of what a differential equation is. Now, in general, solving differential equations is difficult. We offer an entire course, Math 3310, on differential equations. I encourage you to take it. My PhD is actually in studying differential equations, so I think they're quite interesting. But we're not in this course certainly going to be able to solve every type of differential equation, and so we're going to limit ourselves to sort of looking at specific types. So in particular, we're going to focus on equations of this type. And the first thing I want to point out is that this is what we call a first-order differential equation, which is to say that it only involves the first derivative of the function. So this would be a second-order differential equation sitting here because it involves the second derivative of the function. So we're going to restrict ourselves first to first-order differential equations. And in fact, we're going to restrict ourselves further in a bit. But let me point out here, I mentioned before that there are multiple solutions even to this. And because differential equations can have more than one solution, we often refer to their general solutions, which are sort of a whole family of solutions. But we'll sometimes also restrict ourselves further and study what we would call here an initial value problem. So here we have a differential equation paired with a condition that tells us something about our initial value. So I mentioned before that this has the differential equation has multiple solutions. So if you take y of x to be tangent of x plus any constant c, that's also a solution. So we can see that because if we take the derivative dy dx here, the derivative here would be secant squared of x plus c times the derivative of x plus c, but that's just 1. Okay. And so then we have again that secant squared of x plus c, that's my dy dx, is equal to 1 plus tangent squared of x plus c. And again, this is just my 1 plus y squared. Okay. So this is in fact a solution for any value of c to the differential equation. But now if I add in this initial value, that will restrict me to a particular solution here. It'll actually help me find my value of c. So if I then say, okay, I want y of 0 to be equal to 1, then y of 0, well, plugging that in to this equation, that will give me tangent of 0 plus c. And if I want tangent of c to be 1, I need to know what value of c is going to make tangent of c 1. And that value is actually pi over 4. So this implies that c is equal to pi over 4. Okay. And so in fact, here we get the solution to this initial value problem, that y of x is equal to tangent of x plus pi over 4. So while our differential equation by itself admits a whole family of solutions, this initial value problem, which is a differential equation paired with an initial condition, yields exactly one solution. So we often restrict ourselves further to studying these first order initial value problems that have exact solutions here. Now, again, I sort of told you to look at tangent and that tangent would be a solution here. But you might wonder, what if I didn't know that, right? What if I didn't just sort of guess the right solution? How might I solve this? And so what I want to show you is sort of, let's sort of play a what if and see how this works. So what if I treated dy dx like a fraction? Now we've seen this before, right? Sort of with U substitution and some other and trig substitutions. Let's see what would happen if I treated dy dx like a fraction. So if I treated dy dx like a fraction, I could rewrite this so that I get all of my y stuff on one side and all of my x stuff on the other. Okay. So just multiplying both sides by dx would give me this. Then I could divide this over. So dividing both sides by 1 plus y squared would give me this. Oh, sorry, this should be a dx. And then, well, I could just integrate both sides. Now, if you look at this, there are two ways to think about this integral on the left-hand side. You could say, oh, that looks like a trig substitution, and it is. Or you could just recognize that this is the derivative. This integrand is the derivative of tangent inverse. So its antiderivative should be tangent inverse of y. And on the right-hand side, the antiderivative of 1 is just x. And we'll pick up a constant of integration. And now I can solve for y by taking tangent of both sides. And so notice that treating dy dx like a fraction and playing this game actually gives me the right answer, right? Now, we ought to sort of wonder, something about that is not quite right, right? We know dy dx is not actually a fraction. So not only does this first step really not make any sense, I would also point out that this second step doesn't really make any sense because even if you assume that these two things were equal in some appropriate sense, you're then integrating both sides of the equation. And you might say, well, yeah, if two things are equal and I integrate both of those things, then they should still be equal. But you're integrating them with respect to different variables, one with respect to the y variable and one with respect to the x variable. So it doesn't seem like, that's really doing different things to each side. You're integrating one side with respect to y and the other side with respect to x. It's not clear that equality should be preserved in that case. Now, what I'll point out is that if you wanted to be really precise about this, you could, in fact, more rigorously justify this. So what you could do instead would be to leave the dy dx piece alone. You can't treat it like a fraction. It's not a fraction. But go ahead and you can, in fact, divide that 1 plus y squared over. And you would get this. And now integrate both sides with respect to x. So notice that your right-hand side is exactly the same as it was when we treated dy dx as a fraction. It's now this piece that's a little bit different, okay? But now if you sort of think about doing a u substitution, so let u be your y, which is really a function of x, then du will be dy dx times dx. And so this integral would become the integral of 1 over 1 plus u squared du. But if you remember, I mean, my u is really equal to y here. So if I just rewrote this, I could, in fact, just say, well, just call u y instead. And so I still end up here, okay, even though before I sort of end up in the same place as if I had treated dy dx like a fraction, okay? So even though treating dy dx like a fraction is not sort of mathematically valid, it does end you up. It's really just sort of some symbolic manipulation that ends you up in a spot much quicker that is a mathematically valid place to end up, okay? So let's actually think about this a little more generally. Okay. So we've seen that this works for this particular problem, but we can actually do this anytime we have a differential equation where the that's in the form dy dx is equal to some x stuff times some y stuff. So this is what we call a separable ordinary differential equation. So in this case, we have that our right-hand side is a product of a function that depends only on x and a function that depends only on y. And so again, in this particular situation, if I wanted to be really precise about it, right, what I would say is, okay, I can bring the y stuff over. And now I'm going to integrate both sides with respect to x. Now this piece I can do a quick u substitution on. So if u is equal to y of x, then du is equal to dy dx dx. And so this becomes the integral of 1 over n of u du. But again, u was just y, so I could just as well write 1 over n of y dy is equal to this. Okay. And now, assuming I can calculate the appropriate antiderivatives here and here, I can find a generic solution to this differential equation. Now, again, notice that this form down here, which is sort of what I want to end up integrating, is exactly the same as if I had here treated dy dx like a fraction, right? If I had treated dy dx like a fraction, I could take this, multiply both sides by dx. I'd end up with 1 over n of y dy is equal to m of x dx, and then simply integrating both sides would get me here. So often we will use this sort of shorthand to just quickly get to the correct integral we want, even though, again, there's sort of some symbolic manipulation in the middle that maybe isn't sort of rigorously mathematically justified. It still ends us up in a place that is rigorously mathematically justified. All right, so now let's try solving this initial value problem. So we have dy dx is equal to 6y squared times x. And we want it subject to the initial condition that y of 1 is equal to 25. So the first thing we're going to do here is we're just going to focus on solving this differential equation. And notice that this is a separable equation because my right-hand side is a product of just some x stuff and just some y stuff. Okay, so first let's focus on that differential equation. So in fact, maybe I'll work on this up here. So I've got dy dx is equal to 6y squared x. So I want to get all the x stuff on one side and all the y stuff on the other. Okay, so I am going to rewrite this as 1 over y squared dy is equal to 6x dx. Now, you might wonder, well, why didn't you bring the 6 over? I could. There's nothing wrong with bringing the 6 over. I just chose to leave it here. Constants, it sort of doesn't matter what side you put them on. I'm going to leave the 6 here as opposed to moving it over here and having a factor of 1/6 on the other side. Now I'm going to integrate. Okay. Now on the left here, this is really y to the -2. And so if I increase the power by 1 and divide by the new power, I get minus y to the -1, or minus 1 over y. Over here, if I integrate 6x, I'm going to increase the power on x by 1. So x squared and divide by that new power 2. So I'll get 3x squared. And then I'll pick up a constant of integration. Now, my goal here is to solve for y. And so I'm first going to negate both sides. So that will give me 1 over y is equal to minus 3x squared. Now, I could write minus c here if I want. But the constant of integration is an arbitrary constant. So I can also absorb the negative into that arbitrary constant. So I'll just keep that as plus c. And now I'm going to take the reciprocal of both sides. So the reciprocal of the left-hand side will just give me y, and reciprocal of this would be this. And so I get my general solution to this differential equation as y is equal to 1 over minus 3x squared plus c. Okay, now this is a generic solution to the differential equation. I want to solve the initial value problem, however, so I also want to select my constant c that will make y of 1 equal to 25. So let's take a look at that then. So I want y of 1 to be equal to 25. And now if I want that, let's see, y of 1, that's like plugging in 1 for x here. That means I want 1 over minus 3 times 1 squared plus c, right? I want that to be equal to 25. Okay. And so I want 25 to be equal to 1 over c. I've got the c, and then this is just going to become minus 3. Okay. And if I multiply both sides by c minus 3, I get this. And now I can divide both sides by 25. And now I add 3 to both sides. Okay. And I could rewrite that 3 as 75/25, so I can get a common denominator. And that gives me my particular value of c that I want. And so now if I look at this and I want to come up with my final solution here, right? I have y is equal to 1 over minus 3x squared plus 76 over 25. Okay. If you want to clean that up a little bit, you could multiply the top and bottom by 25. That would give you, that won't change the value because I'm doing the same thing to the numerator and the denominator, but it would give you minus 75x squared plus 76, maybe a little nicer form, I don't know, but either of these are equivalent. Okay, but using my integration, I was able to find a particular solution to this initial value problem. Okay. Now, an important sort of use of these, I mean, these differential equations are very, very interesting mathematically. I study them sort of as purely as mathematical objects, but also differential equations are very useful in a lot of different applications, particularly in the sciences. Okay, and so what we want to see is sort of how differential equations arise in those applications, and then how we can use our methods of integration and what we've learned so far about these types of differential equations to answer questions in sort of the real world. Although these equations may seem relatively straightforward to solve, they actually have pretty wide applicability across the sciences. So if I look at this first type of equation here, this can be broken into two cases. So these sorts of things often represent uninhibited growth or decay. So we get uninhibited growth when K is positive, and we get uninhibited decay when K is negative. So often where you see things like this arising, so you could imagine, for example, a bacterial colonization that grows at a rate proportional to its current population size. So this would be like Y of t would be the amount of bacteria, X would be time, and the derivative of the population size with respect to time is equal to some constant, some positive constant, times the current population size, right? So as the population gets bigger, it grows faster, right? So that gives us the uninhibited growth case. You can also think about things like radioactive decay. So certain radioactive isotopes, right, they decay at a rate that is proportional to the amount of the isotope that's currently there. So in that case, your amount, Y would be like your amount of radioactive isotope, X would again be time, and the derivative, the rate of change of that radioactive isotope is negative because it's decreasing. So, but it's proportional to some negative constant times the current amount of that isotope. Now, you can also get these inhibited growth and decay cases. So imagine here for a second that K is positive, okay? So if K is positive and Y starts out above this constant value T, so I'm imagining this capital T is some constant value. So if Y starts out above this constant value T, then this will be negative, this is positive, so I will decay, and my derivative will be negative, and it will decay down to t. So if Y is bigger than t, we'll get decay to t. Okay. If, again, assuming k is greater than 0, if I start with Y less than t, well, if Y is less than t, then this will be positive. Again, K is positive, and so I'll be increasing, but only up to t. So in these cases, I get sort of a growth and decay, but they're sort of inhibited at this level t. Now, you'll sometimes see, and it doesn't really matter what you do here, you could also represent this as some constant times Y minus t, and then it would just switch for when K is negative. And you can also allow K to be negative and see what happens. But again, you get in these sort of growth and decay situations, you can see that these differential equations can model those very well. So I want to look at two particular problems and see how we can use differential equations to help us answer some questions here. All right. So in the first problem, I want to think about the antibiotic amoxicillin. It's a penicillin-derived antibiotic. And if you look at the amount of amoxicillin that's in the blood, amoxicillin is both broken down in the body, and it's also excreted through your kidneys. And that sort of decay rate overall decays at a rate proportional to the concentration that's in the bloodstream at any given time. And so imagine that you took a blood panel and it indicates that the concentration is 6 micrograms per milliliter. An hour later, you do another blood panel and it indicates that the concentration is 3 micrograms per milliliter. Okay. So the first thing we might want to think about is sort of, how does this, how could we represent this situation in using this language of differential equations? Okay, so the first thing I want to do is I want to try and find an equation which models the concentration of amoxicillin in the bloodstream. Okay, so in general, I can sort of think about, okay, I want to know how the amount of amoxicillin, so I'm going to call that capital A, is changing with respect to time. Okay, again, it's sort of important to keep track here that A of T is the concentration of amoxicillin in blood at time T. Now, what we were told is that it decays at a rate which is proportional, some constant of proportionality, to the amount of amoxicillin that's actually in the blood. Okay, so we have sort of this sort of equation. Okay, now this looks like just sort of a regular, this is a separable differential equation. Okay, so I can actually rewrite this 1 over A dA is equal to K dt. And now I can integrate both sides. This will give me natural log of A is equal to, this will give me K times T plus C. Now my goal is to write down an equation for A, the amount of amoxicillin. So if I exponentiate both sides, right, I will get, I'll get A is equal to E to the KT plus C. Now, I can actually do a little bit of work to help myself here. I'm going to leave the A alone for a second. This will be, I can rewrite this as E to the C times E to the KT. Okay. Now, notice we're probably used to thinking about this the other way. If I have same base, different powers multiplied together, I add the powers, right? And so that's just, I'm using that rule of exponents in reverse to sort of go from here to here. And the reason I'm going to do that is because then what I can do is recognize that, well, C is some arbitrary constant. So E to the C is just some arbitrary constant. And I'm going to call that constant momentarily A0. Okay, and we'll see why I'm going to call it A0 in just a second. Okay. All right, so now this is all great, except this doesn't really give me an equation yet which models the concentration of amoxicillin in the blood because it has these sort of constants K and A0 here. I'd like to figure out what those constants are so I can have sort of a precise mathematical formula I could use. Okay, so let me recall a couple things that the problem also gave me. I was also told that when an initial blood panel was done, let's say that was at time 0, okay, that the concentration was 6 micrograms per milliliter. Okay. Now, the units aren't particularly important as we're sort of plugging things in here, except to remember that these things do have units. So T, the way we're going to do this is T is going to be the time in hours, and A is going to be in micrograms per milliliter. Okay. So again, it's sort of not important in the mathematics, but in interpreting the mathematics, it will be very important. Okay. So if I want to, oh, sorry, I was also told then that after 1 hour, the concentration was 3 micrograms per milliliter. So I want to use both these pieces of information to see if I can solve for these constants. Well, if I use the first piece of information, so A of 0. So if I look here, if I plug in T as 0, well, I'll get e to the 0, that's just 1, I'll just get a 0. Okay, so that's actually why I called this A0, because when you plug in T is equal to 0, you just get A0, and that amount is 6. Okay, so I can sort of use that to update and say, okay, my A of T is 6 times e to the kt. Okay, but now I'd still like to figure out what that k is, so let me use this A is equal to 1. So I look at A of 1, now I know that is 6e to the kt, or sorry, 6e to the k times 1, so it's just 6e to the k, and I want that to be equal to 3. Okay. Well, now I'm going to take this equation and solve for k. Okay, so divide both sides by 6. That'll give me e to the k is equal to 3/6, or 1/2. And now I'm going to take a natural log of both sides. Okay, if I take a natural log of the left-hand side, I'll just get k. And I get k is natural log of 1/2. And so now I have that my A of t is 6e to the natural log of 1/2 times t. Now I could be done here, but I can actually use rules of exponents to simplify this even a little bit more. I could rewrite this as 6e to the natural log of 1/2 whole thing to the tth power. Okay, you normally see this as like if I have something raised to a power, whole thing raised to another power, I multiply the powers together. So again, usually we see this in reverse. But the reason this is helpful here is because I can then recognize that e to the natural log of 1/2 is just 1/2. And so I get my final model here that A of t is equal to 6 times 1/2 to the t. Okay. All right. Now, that's all fine and great, but you know, why might I want such an equation? Okay. So now let's sort of ask another question. So I get this erased here. I'll leave down here our model so we have it's sort of sitting here. So this model is telling me what the concentration of amoxicillin is in the blood after, you know, time t after that initial blood panel. So now imagine that first blood panel was taken right after a patient took a dose of amoxicillin. So you're maybe like, you know, very, very shortly thereafter. So what you're really seeing is the concentration of amoxicillin in the blood, you know, right after taking a dose. But imagine that, you know, you want to know when you need to time the second dose. Maybe we know that blood concentrations less than 0.025 micrograms per milliliter aren't clinically effective, right? So we want to make sure that the amount stays above that number, okay? So I might want to make a prediction as to when a second dose may be needed, okay? So in that case, I might want to know, well, when is the concentration of amoxicillin, when is that going to become less than 0.025, again, micrograms per milliliter, okay? So in that case, I just plug in what I know A of t is. And now I could just do a bit of algebra. And so I'm actually going to sort of wait because I'll just plug everything in a calculator at the end. If I divide both sides by 6, and then if I take a log base 1/2 of t of both sides, now when I do that, that's actually going to flip my inequality because log of a base less than 1 is a decreasing function. So I'll get t is greater than log base 1/2 of 0.025 over 6. You can plug that into Desmos or any sort of calculator you have, and you'll get that is roughly 7.9. Okay. And so what is that telling me? That's telling me when time goes beyond 7.9, the concentration is going to drop below 0.025. And again, this is where units are important. My time is in units of hours. So after roughly 8 hours, right, a little bit less than 8 hours, the concentration is going to drop below 0.025. And so you're going to need to take another dose. Okay. So we can see that these sorts of models can in fact be used to help us understand real world problems. And really the benefit here is that it doesn't require if you think about this particular context, right? One thing you could do is just keep drawing blood and keep drawing blood until you see that the concentration drops too low. If you think about that from a patient perspective, you probably don't want somebody drawing blood from you constantly. So in fact, many physicians do use, usually they don't use the differential equation, they would use sort of this sort of formula at the end, but they use these sorts of formulas to help understand when they might need to administer additional doses of certain types of medication. This is, by the way, for standard things, right? They just know, give amoxicillin every 8 hours. But for patients who may have, for example, reduced kidney function or other bodily functions which aren't working properly, there are often these more complicated formulas which are derived from these sort of differential equations that help them understand how to dose medication effectively. All right, we're going to look at one more application. So imagine that a soup is made by boiling some stuff, some meat, vegetables, and some broth. And it's recommended so that you don't burn your mouth that soup should be eaten at about 150 degrees. You could probably actually eat it a little hotter than that. A little cooler than that would probably still be fine. But let's just say for calculation purposes, 150 degrees. If the ambient temperature of the room is 60, let's say the ambient temperature of the room is 62 degrees, and you take the soup off, it's been boiling point's 212 degrees. This is all degrees Fahrenheit. You take the soup off, you measure the temperature 3 minutes later, and it's 200 degrees. And you want to estimate about how long it's going to be until the soup reaches 150 degrees so that you can serve it. So one of the important laws in play here is something called Newton's law of cooling, which says that the rate of change of temperature of an object is proportional to the difference between the temperature of the object and the ambient room temperature. Okay. So let's use Newton's law of cooling first to think about sort of what is the model of the temperature. So this says the rate of change of the temperature, which I'm going to call capital T, the rate of change of the temperature with respect to time, is proportional to the difference between the temperature of the object and the ambient temperature. Okay, so let's call T, capital T is again the temperature of the object, and we're going to call the ambient temperature or the room temperature T sub A. Okay. All right. This is now a perfectly good separable differential equation. I can divide the T stuff over. Multiply both sides by dt, d little t, and I get this. And now I can integrate both sides. Now, if I integrate this side, I'll get natural log of t minus t sub a. If I integrate this, I'll get kt. And of course, I'm going to pick up a constant of integration. If my goal is to solve for capital T, I'm then going to exponentiate both sides. And just like before, right, I can rewrite this in this way, and now I can just relabel this. I'll call this, let's say, so T minus TA. I'm going to call this for the time being capital. We'll call this capital S. Doesn't really matter what I call it. I'm not going to use A because it might get confusing with the subscript here. E to the KT. Okay, but I'm just going to relabel this E to the C as S, and then I'll get that T is equal to S E to the KT plus T sub A. Now, in my particular case, I know what the ambient temperature is, right? I know that the ambient temperature is 62 degrees. So I'm going to want to make use of that, right? So I already know that the ambient temperature in my particular case is 62 degrees. Okay. And what else do I know? Well, I know that the second I take it off the stove, it's boiling. So it's 212 degrees. Okay. I'm also told in the problem that 3 minutes after, it's down to 200 degrees. Okay. And so what I can do here, right, is I can use these two values to solve for these constants S and K, just as we did before. Okay. So what I actually want to do here is I want to pause, and I want you to see if you can use these two values to solve for the constants S and K. All right, so you should have been able to do that, and we should have gotten that S is equal to 150. It's actually just equal to the difference between the initial temperature and the ambient temperature. So it's 212 minus 62, which is 150. And now K is a bit more complicated. K is 1/3 natural log of 138 over 150. And so I get that this is my model for the temperature at time t. Okay. Now, if I go back to sort of that original question, right? The original question, which might be hard to see when I flip over here. The original question was basically how long until the temperature reaches 150 degrees? Well, now I can do something very similar to what I did before. I can say, well, I want to know at what time will my temperature, oops, too high there. At what time will my temperature T of T be less than or equal to 150 degrees. And now I simply plug in 150 e to the 1/3 natural log of 138 over 150 times t plus 62. And now I want to just solve this equation for t, or this inequality for t. Okay, so again, I'm going to pause the video here and let you see if you can find the correct value of t. The video will actually end after this, so the question will pop up. You'll need to work through to calculate the correct choice of t. It'll be very similar to the way we solved it in the last example. And so see if you can find the correct value of t. So you should end up with something like this will, when t becomes greater than some number, then the temperature will be less than 150 degrees. Okay, so we'll sort of pause things there, see if you can find the value of t. You'll then have opportunities in the homework and a quiz to practice more problems of this type.